Hello. I get the occasional email from somebody saying like, "Oh, I'm sick. I'm not going to be in class." I really appreciate getting them, but you all are grown-ups. If you feel sick, please stay at home. This is why I record the classes. This is why the slides are online. This is where you can do everything on Blackboard. Because hey, life happens, and especially if you get sick, let's not get the rest of the room sick. Perfectly okay if you stay home once or twice. All right, so today we're going to talk about distance scales. So we talked about gravity, we talked about light. Like from light, we learn everything about the universe. From we learned that gravity essentially rules most of it, and then the last ingredient is the scale of the universe, or the scales to the stars. The fact that there's such unimaginable distances, and that English words sort of run short of that. And so we learned that we can sort of measure the distances in our own solar system now thanks to radar. There were other tricks before that, by the way. Like people cleverly figured out that, for example, if you measure the transit from Mercury, you can, across the sun, you can actually get the distances to Mercury and the rest of the planets. Like people have been trying to get accurate distances, for example, by different positions, by using parallax in our solar system for quite some time, but you can get it really, really accurately using radar or lasers. And so, remember when we talked about tides, that the moon was moving away a little bit because of the friction that the ocean is enacting on the tides, the fact that the bulge has to keep up. So that transfer of energy means that the moon moves out about 4 centimeters a year. That you need a really accurate distance for, right? So that's what you get from these laser measurements. And so we talked how we can, once you have a distance to a star, because you then know, like, okay, that kind of star, and there's a different one that's much dimmer, I can actually get their relative distance from their apparent, how they look to us, and their absolute magnitude. And then we briefly got into Cepheus and the distance ladder, right? So this is the last part. And so next week we'll talk about observations in the sky, moon phases. We are going to look at the night sky. So yes, this one beautiful dome is going to be very much good use to us. So how do we measure these? So these are sort of the incremental distance, like as you go from radar astronomy, this is what you mostly do in their own solar system, and even really not that far from us, right? So parallax is what we use for the nearest stars. Magnitudes is what we use for the stars even further. Standard stars, Cepheus is what we use further than that. Standard candles like supernova and redshifts are for even further than that. So we bootstrap our way out of this. We calibrate one technique with the one that we max out to get to the furthest distance. So what is the yardstick in the solar system? The distance between the Earth and the Moon, the distance between the Sun and Jupiter, and you are whipping out your voting cards at this point. The distance between the Earth and the Sun, and the distance and the diameter of the Sun. What is the yardstick that we use in our own solar system? Voting in 1, voting in 2. Don't worry about looking back and seeing what everybody else votes, just vote for yourself. All right, I'm seeing massive numbers for C, the distance between the Earth and the Sun. And so the inverse square law for apparent brightness gives us a relative distance or an absolute distance. Can I get an absolute measurement, or do I know how relatively they are? Voting in 1, voting in 2, and voting in 3. All right, I've got majority A and relative distance. Yes, I can tell how far they are with respect to each other. A star has a parallax of half an arc second. How distant is this star? It's 5 parsecs, it's 2 parsecs, it's 6 light years, it's 3.26 light years. Remember how this went? 1 over the angle, the angle of difference, right? Voting in 1, voting in 2, voting in 3. Everybody, pick your best number, pick your best. Yes. Oh, it's almost an equal distribution of B and A. I know what happens now. It means you turn to your neighbor, and even if the two of you agree, explain to them why you think the answer that you picked. You have about 90 seconds, and then we'll vote again. question on the way here. Voting in 1, voting in 2, voting in 3. Did you convince your neighbors? Oh yeah, you did. All right, I see majority B now. If you divide 1 over half, how will you get? 2. So that means if it's a half arc second in difference between July and January, if I see them star move that much, it's 2 parsecs away. And you go like, but there are no stars 2 parsecs away. Funny you should mention that. Yes, the ones that we can see, the nearest one is Alpha Centauri. But more recently, we found a couple of italy-piddly brown dwarfs that you don't see in the visible, but you can see in the near-infrared, and 2 of them are about 2 light years away. So we have closer stars now. The discovery was in 2013. It's kind of odd to think that the nearest star was found in your lifetime. That feels wrong somehow, but yeah, we discover stuff nearby all the time. So Alpha Centauri is 4.26 light years away. A radar pulse to measure the distance would take 4.26 years, 8.52 years, unknown, or 3.26 light years. Voting in 1, voting in 2, and voting in 3. Getting majority B vibe. Yes, it would take the radar pulse 4.26 years to get there, bounce off Alpha Centauri, and 4.26 years to get back, so it would be double the time. Yeah, it would take all of middle and high school for your middle school science project to come back. Right, so this is why we don't do this. So if an apparent, oh, we did this one already. So if we compare, like, if the apparent and the absolute magnitude are the same, then it's put at 10 parsec. Like, that's how we define the absolute magnitude. If the apparent magnitude is a lower number than the absolute magnitude, then it's within 10 parsec. Considering this is literally a half dozen stars, we don't have to worry about this. But if the apparent magnitude is greater than m, then the distance is 10 over 10 parsecs. So these are this is the way that you can measure. And if you kind of wonder, it's like, what's the little v doing here? We put that in there to remind ourselves if it's the which color we've actually measured the magnitude in. So the apparent magnitude minus the absolute magnitude, that is the distance module. We call that the distance module sometimes, but that's the difference that comes from putting the star further away. So if you know the absolute magnitude, you can figure out what the distance is. So if I rework this, I get the distance is 10 to the power. You know how to do power to the power in your calculator. There's a little 10x thing, and so that's the one you need to use. I don't know, I never assume anything about what everybody's learned to use their calculators. Some people go like, of course you have a Texas Instrument calculator. Like, no. So you have the apparent magnitude, the difference between the apparent magnitude and the absolute magnitude, plus 5, the whole thing divided by 5, and you do 10 to the power of that, then you have that in parsecs. You get that distance in parsecs. So that's a good way, as long as you know what the absolute magnitude is. And so before that, we needed to get parallaxes to that. So that is that 1 over, this is the parallax angle. So the distance in parsecs is literally 1 AU over that angular distance difference. And with the Gaia satellite, which literally stopped working earlier last month now, so midway in January, the mission stopped. I think they were basically running out of fuel, but they have measured the distances to all these different stars. And so just to give you an idea, it's like instead of arc seconds, so a 60th of a degree, and a degree is basically your arm, the pinky sticking out at arm's length. So a 60th of that. That's pretty good measurement. Like that's sort of the limit that you can do with the eye and like a good eyepiece sort of looking where things are. So this is 10 micro, so a millionth of that. So that is, let's see, that is the equivalent of a human hair along its axis subtends about this angle. How far away would it be? So the diameter of a human hair is about 15 microns. So a millionth of a meter. And so you can put it at 1,000 kilometers, and that's the distance. Like, yes, Gaia can split a hair, all right. And so you can get a good distance out to 100,000 parsec, which, when we think about our Milky Way, that is sort of a good distance to do a good chunk of it. But how did we do distances before we launched Gaia? Well, we used those variable stars. And fun fact, so here in the center sits the North Pole, the pole star. We'll talk about that next week. And as you take a really long picture, like if you take a picture and you leave the camera sitting there and taking the picture for hours, then basically all the stars rotate, look to rotate, basically we rotate underneath them. And you can see these star trails in these long exposures. You know, people do this when they're at the telescope and then they have their camera out and make these star trail pictures. But there's a star in the middle there, that's the pole star, and that's the one that doesn't rotate. And so that is also a Cepheid variable. And to just give you an idea what a Cepheid variable and how violent of the thing that actually is, it is pulsating, and as it's doing that, it sort of, every time it pulsates out, it actually ejects a little bit of its outer atmosphere. So that's what you're seeing here. These swirly clouds are the things that are being ejected from this Cepheid. So it is quite a magnificent thing, and also quite useful, as we found that, basically Henrietta Leavitt found, that the pulsation time and the absolute magnitude are directly related. So I love showing really old plots from what people were doing, you know, beginning of the 20th century. So this is some of her plots on how many days, what the magnitude was, and she did this on photographic plates, so she had this sort of like monocle and actually measured how, each individual brightness of the stars for each new plate. And she found that, you know, these are the different stars and they have this weird sawtooth diagram, right? So this is her line drawn through it. And so she noticed that the pattern repeated. It was a very steady pattern that that Cepheids had, and so for the given period, you can actually tell how much brighter they were. So the brightest Cepheid variables had longer periods. So if you get to 100 days, which is about 3 months, so essentially, if you follow something for the entire school semester, then yeah, you can sort of see that it goes through one period. But if you go a little dimmer than that, you get something that, you know, pulsates in a week. And so consider two Cepheids, the same apparent brightness. So they look the same brightness. Star A is a 6-day period, and star B is a 30-day one. Which one is the brightest? Voting in 1, voting in 2, voting in 3. Okay, so for this, they look the same brightness. Which one is the furthest away? Voting in 1, voting in 2, and voting in 3. They look the same brightness. Okay. We're going to do a walk around. Read the word thing again. Talk to your neighbor. Turn to your neighbor, even if the two of you agree. Explain to them why you gave your answer. All right? That made sense. Voting in 1, voting in 2, and voting in 3. Seeing solid B almost. Okay, let's walk through. First thing, they look the same brightness to us, right? So one of them has to be further than the other because they're pulsating at different periods. With me so far? Okay. Well, it starts with the 6-day one. So that's about here, 5 and a bit. Go up, do the yellow line, go left, that's about -3. I'm rounding up because that's okay, right? So absolute magnitude of -3. Yes? All right. So star A has an absolute magnitude of -3. Star B is 30, so 20, 30, that's about here. Go up a little bit, stay over this line. So -6, maybe not quite, but let's just say -6. Let's see, which way do magnitude go? The lower value means brightest. So B is the brightest. We all agreed on that first. So if B is the brightest, inherently brightest star, and A is an inherently dimmer star, but I'm looking at them at the same brightness, then B has to be further away. So you all work that out, fantastic. Thank you. So this is how we figured out how distant Cepheids work. And so you can measure that, and you can actually calculate out those distances. As soon as you have a period, then you get your period luminosity. You can either read it off of the line here, or you use the line that we fit through it, which uses that log of the period in there. So yeah, here it is. So if I want the absolute magnitude, I say, okay, I want the 10th, you take the period, 5 days, say, you take the log 10 of that. There's the natural log, there's the log 10, and I use log for the log 10. So you take the log 10 of that, multiply that times -2.78, and then subtract the 1.35, and that gives you the absolute magnitude. So if this value gets bigger, then this whole thing gets bigger, you get a lower value, you get a brighter star. And so I can take that absolute magnitude, I have my apparent magnitude, I can put that in here and get a distance, that gives me the distance in parsecs. If I then want to put it in a newspaper article, because no one else uses parsecs except us astronomers, we actually multiply by 3.26 and say, it's this many light years away. So if you ever see a newspaper article and it goes on about a galaxy that's like millions of light years away, none of the astronomers actually put that in their paper. Someone just multiplied that by 3.26 because they were like, people have heard of light years and no one has heard of parsecs. So there we are. And so I have a Cepheid distance project for you. So yes, this is a part where we do a little bit of math because I've just walked you through every step of how to do that. This is not scary, this is perfectly fine, but it is how you're following the footsteps of Henrietta Leavitt in the large Milky Cloud or the large Magellanic Cloud. Depends a little bit on who you talk to, how you want to name that. So I put the large Milky Cloud on top of Magellan. I find it a little odd that we call these things the Magellanic Clouds because I don't think Magellan survived the trip that he supposedly had seen them on. So it's a little bit odd that you say, oh, this is the Magellanic Cloud. I mean, the people who lived in the southern hemisphere had known about these things for tens of thousands of years, so it's odd to name it after the guy. So I like the small and large Milky Clouds, because Milky Clouds seems like a much more fun thing, possibly coffee related. And let's see, so this is your group work. Again, you can work through it on yourself with as long as you add something in with your nearest group here. And you kind of wonder, it's like, okay, what are we doing here? Remember that this is supposed to be a science class. So part of that is I'm giving you the raw data, and we're working all the way through. We're figuring out every piece that we can figure out from this. And yes, the equations are a part of it, so the equations are in there. All right. See how we do. I'm going to set a timer. Walk around, answer questions. So you see what time we actually get rid of them, and when do you see the pattern repeat itself? So there's a flip, there's a outlet. So what's the difference between Can you imagine why there's weird gaps in that? Can you imagine why there's a gap here? You observe this only at night. So you have to wait over a day, there might be clouds. Yeah, you get good data, bad, cloud came by, oh, it's, so instrument doesn't work. You get, this is real data, right? So this is where, part of the science class, right? We're going we're looking critical at this plot. We go why is it look like that? Why are we like, what are the steps that we need to do in order to analyze it? So, nice. All right. Any questions? Anybody stuck on it? Completely super. Okay. We'll go over the whole thing, but I'm curious what you. Yes. Yay. Questions. Please ask me questions. All right. So we saw Levitt here. So if you want to figure out what the period is, you wait for the pattern to start repeating. So you want some nice, easy to identify. For example, where it starts going back up. So, okay, here. It's like a minus, 3 days? And then it does it again at 4 weeks. And so that's 43 days. And I'm like, actually, I'm not sure I can read this off right. So maybe I'll start at the tip here. The point is missing. So when does the point repeat? Oh, the point repeats over here. So So it's 40 and 3 days, yeah, 43 days. It's a 43-day period. This one, however, I go like the tip is over here, and it's a little short of that, so it's like 32 days maybe. So that gives me a cool. So the first peak is at 2 days, and then it's the second peak. Yes, minus 2.78 times the log of 10 of the period minus the 2.75. I try to be a little clearer than the slide. I've confused people. Aha, significant figures. All right, this is part of the whole deal. What do you feel is a good number to give me? Right? So, where are we at? Did anybody get a distance yet? You got a distance? You're all working still, so just keep working. The top, that's the maximum. And you've got new line, so that's the bottom. And so where is where is sort of in the middle? So where if you go a line where you have both the same numbers of both as well as same number of points. So it's like that's the bottom. So peaks and valleys, right? So where's the lowest point and where's the highest point? And so you sort of take the highest and lowest point, you're like, where I'm sitting in the middle? That's my average. Why am I doing this to you all? All wondering. I'll get to that in a second. Simple error management, figure out how to do the absolute management. Alright. I'm getting questions about significant digits. How far along? I feel like most of you are on the last question or the second to last question. It helps me always to actually write down where the numbers go. So that before I put it in. All right. See people calculate their distances. I'm going to explain the thing that my professor always asked me. He was Italian. He would go, "Why are we doing this?" most dreaded kind of thing that you could do in the middle of your talk. Why do I care? Well, none of you, or very few of you, are going to observe a Cepheid and figure out the distance to that star. Yet this is a useful exercise, hopefully in a more metaphysical sense, but sort of somebody is going to present data to you, and that information is going to be important to you, right? Somebody's going to give you a graph, and now you're going to have to glean some information out of that graph. This is a typical exercise of that, right? Somebody might give you like, here's your growth of your pension. None of you care about pension just yet, but you will in due time. Or something else, right? So somebody will give you data in graph form, and now you have to sort of interpret that. And there's a few things that that's what we're doing here. First thing is, how many data points do I even have? How good is this data, right? So first question is, how often has this been observed? There's 25 points in the whole plot, right? There's literally we've shot how bright this thing is 25 times. We just had here a fun discussion. Why aren't the points equally spaced? That could have been another question. Now, if you imagine, this is being done with a little telescope on a mountain, so when it gets daytime, you don't see the star anymore. So you go to bed and wait for nighttime to fall so that you can take new observations. But there could be a cloud, right? So this is all weather and daylight dependent. So you get weird gaps between your data, even if it's, especially since it's about a week's worth, 10 days worth of data. Okay, so if I then want to estimate what the period is, I don't have a neat little line going through it. I have to draw it in my mind's eye, right? I have to draw the fit myself. So it's like, how many peaks do I see? There's one peak, and there's a second peak, and then it goes down, but I didn't actually get it all the way down, right? So there's only, between these two peaks, there's two peaks in there, and one is roughly at day 2, and one is roughly at day 7. So the period is 5 days. Can I estimate that to any more precision than 5? Can I say 5.1, 5.2? Anyone who's been 5.256? You don't have that level of accuracy. You can just sort of go 5. That's as good as it gets. You don't have a lot of more information than that, right? If you start saying 15 digits after the decimal point, I don't believe you. You could have not measured that accurately. But 5 works. We can just hold that in our heads. Then you're asked, what's the apparent magnitude? Now, here's another one. And every class, I have one person who goes, oh, I know what to do. I'll measure every point and stick it in my calculator. So all 25 points, I put them together and I divide by 25. But this is where this gets mean. I don't have 2 perfect periods. I'm missing a couple of low points over here, so I would bias myself. Now the best thing to do is eyeball this puppy again and go, all right, top's over here, bottom's sort of over here, so 12.2 and 16. This is about the mean. Can I do this any better than 15.6? No. Again, I don't have a ton of information. It barely goes through one cycle, and really I should have waited a couple of months to actually get the next periods to get that really accurately. Fine, I have a good reason to go back. But that's how you measure. You can go like, well, this is where it seems to go up and down over around the 15.6. So the apparent magnitude is 15.6. That's pretty good. With me so far? An agreement that that's a good measurement. Period is 5 days. Apparent magnitude is 15.6. All right, that's all I need to know. There's a calculation how to get the absolute magnitude. It gets you to about -3.3. And if you start filling out any more detail, remember that we didn't get the accuracy of the period more than 5, so that didn't have any decimal points behind it, and you probably don't have to carry more than 2. So it's like, yeah, -3.3 is probably fine. And so if you then stick that in the calculation for distance, you get about, who has them? Just ask answers. What did you get at? How many parsecs do you get if did your numbers agree with what I just said? If not, why didn't they, like, what was your thinking? Where went your thinking astray? But you get about 60,000 parsecs, right? So that is 60 kiloparsecs, which happens to be the distance to the Large Magellanic Cloud. Now, if you're being really devious, you would go, oh, but I Googled the distance to the Large Magellanic Cloud and I'm working backwards from that. No, that's not what I wanted you to do. It's not like I'm jonesing for the accurate distance for the Large Magellanic Cloud. We know this, right? There's people have been looking at that for literally 100 years. What I was hoping you would do is go, I'm being presented with data. The data isn't fully complete for a full 2 periods, but I can estimate what the mean is, I can estimate what the period is, and I can use what I've learned from the data. That's the sort of one, meta I find a really weird word, but it's like, I want you to take that away and use that in your life later on. Like, this is why this is a general ed science class. Like, I want you to do stuff like this. So just explaining that. Because let's face it, none of us, including myself, are going to be doing this for a job. But it is a hopefully useful skill. So, what did we do with those Cepheids? Well, you may have heard of this chap called Hubble. We named the Space Telescope after him. And so in the 1920s, he used the Cepheid variables of Andromeda and then a couple others by showing that, yes, that was a Cepheid. It has the kind of periods, but in order to get to that dimness, if you get a star that dim, this whole thing would have to be outside our Milky Way. It got a distance that was clearly much further than our Milky Way was in size. And so that meant these little fuzzy things that turned out to have Cepheids in them weren't little smudges somewhere in the Milky Way, glowing balls of gas or spirals of gas, but they were in fact outside our Milky Way. And so 11 weeks from now, when I'm talking about the entirety of the universe, this is suddenly when our universe blew up to way bigger, because all those things turned out to be outside our Milky Way and Milky Ways in their own right? So suddenly slightly over 100 years ago, we realized that the universe was much bigger than we thought. Okay, what he also figured out is that we talked about redshift not too long ago, and so he noticed that their lines were shifted, they were all moving away from us, and so he noticed that both the distance, and so this is the velocity, and this is the distance in parsecs. You can sort of see, because somebody has neatly written that down there, and so you notice that there was a sort of a linear relation between that, meaning that if you take the redshift of the galaxy, you get its distance. So redshift helps you for galaxies to get a reasonable distance, but also everything was moving away from us, and that has some big implications for how we see the whole universe. It's not because the Earth is smelly and everybody wants to get away from us, it is the fact that everything is expanding. So this had a bunch of implications, but for us, the interesting thing is, if we now want to get a distance to a galaxy, we can measure its redshift. That's easier to do than trying to find a Cepheid in that thing, repeat observations, and really that Cepheid trick only works if you can resolve the Cepheid, and it works with a space telescope for a few nearby galaxies. So it sort of works, but for nearby stuff. So using the redshift allows us to get us the distance. So redshift now becomes a shorthand for most extragalactic astronomers, and that's the kind of flavor of astronomer that I am, which we just say redshift instead of distance. That's the distance for that galaxy. We measure the redshift, and because of Hubble's law, we know how fast it's moving away from us. It means that it's that far away. And that is called Hubble's constant, because naming things after yourself is fun if you discover them. And so we have Hubble's constant is basically you measure this velocity, that is the Hubble constant times the distance, or if I want the distance, that's the velocity divided by the Hubble constant. Now here's the funny part. He got the actual value for the Hubble constant completely wrong. He started with 500 kilometers per second, so it expands that much for every megaparsec that you go further away. So we have this really weird unit called kilometers per second, or velocity, over megaparsec. So the unit is the speed over the amount of distance. This is the current value that we sort of are accepting of, so it's basically about 10 times off. And if you go like, well, that was quickly corrected. No. When I started astronomy in undergrad, we knew that the Hubble constant was somewhere between 50 and 100. And you wouldn't believe the fight fights that we had about what the unit actually, what it actually was. And so it only got settled when the Hubble Key project got done. And so for about 20 years, I was like, oh, great, the Hubble's Key project has happened. We don't have to worry about the value of the Hubble constant. No, fun fact, this is the Key project, the KP, and it measured at just over 70 with a pretty big error bar, right? So if you're reading scientific plots, who has seen error bars in plots before? Do you know what they mean? It means that the measurement cannot really contain it so that's 2/3 of the time it should be in here. Could be still outside, but we're pretty confident it is in this range, and that's the value that we measure. And so as we got better and better and better distances, so you see all these different projects with the Hubble Space Telescope mostly, our error bars started to shrink. The actual value moved up a little bit, but that's okay. And this is sort of where we ended up in 2016, and pretty much where we've been since with Cepheids. Now, there's a completely different way of doing this, is looking at the very early light of the universe, and it also measures the Hubble constant, the level of expansion for the universe. And this is the values that it found. And at some point, you notice that these error bars don't overlap at all. So this group is saying, the red team is saying, well, it has to be here, and the blue team is saying, well, it has to be here, and they can't both be right. In fact, they just sort of went, all right, one of us has to be wrong. Here's our data, we'll take yours, and we'll do the exact same analysis and see how you do. And the answer was, no, you did everything right. Your answer is just different from ours. And if you've ever had that on an exam, you know one of us is in trouble, possibly both of us, right? If we both got our answer wrong, but we're not even in agreement with each other. So we're right back where the controversy started, which is like, what is it? And so I'm excited about this. We'll end the actual semester on this slide, where it's like, yes, this is the current controversy. There's a couple of more points since, but we've been trying to measure how fast the universe is expanding ever since. And so, yes, this is what we do, Cepheid distances with the James Webb Space Telescope. This was year before last. It was the very first, one of the very first things we were doing. You can see that this spiral galaxy has all these little stars in there. And as you go closer and closer, we want to go see what these Cepheids look like. And so if you do this with Hubble, Hubble has big pixels. It's an older camera. And I never have to explain why older cameras have big pixels anymore. This is wonderful because you've all have gone through at least 2 generations of iPhone or phone or what have you, right? So you looked at your pictures and like, this now has 1 more megapixel more. The Hubble hasn't gotten a new camera since 2005, so it has bigger pixels than James Webb, and also because it's looking in the optical, when we talked about wavelengths, it's literally looking at the light that we're sensitive to. It's seeing a couple of big stars, it sees a whole bunch of stars, and so in here somewhere is that Cepheid, and you see it go brighter and dimmer. If I look at the exact same Cepheid, I can tell the stars better apart because I've got smaller pixels and I'm actually focusing better, and because it's near infrared, everything is sort of not in big blobs, but so there's my Cepheid. You can actually isolate the Cepheid better, so you can measure its brightness better. So that's what it's been doing. So all the error bars shrink a lot in the error period, and apparent magnitude plot becomes a lot cleaner. And so we can measure things better with James Webb. And so we're trying to knock that last uncertainty out of the Cepheid period luminosity diagram. So it's still what Henrietta Levy did 100 years ago. That is still cutting edge science. We were doing it last year. 2023, but that was the first result from that project. They're still working on it. So her idea, her result is still actively being worked on. So if I now ask you, in ranking in order of like distance that I can use, ranking in order of maximum distance you can use, where do you start, right? So redshifts to radar astronomy, redshifts to Cepheid, radar astronomy to redshift, Cepheids to supernova. All right, read this through for a sec, and then vote on what you think maximum distance of utility, right? So what's the one that you start with, the one that's the shortest distance, and you end with the one that you can use very, very far away. Voting at 1, voting at 2, majority C answer. Let's turn around what that actually says. All right, radar astronomy. You're right. That is absolutely the one that doesn't go very far because we have to wait for the pulse to come back. Parallax works if we actually look at a star, we can actually see it move. Even with Gaia, that's really only in our Milky Way. Cepheids, we can go to the nearest galaxies. With supernova, is even those are as bright as our own, as the galaxy that they're in. And then redshifts is the furthest that you can go. So well done on that. So the distance ladder. So this is sort of how we think of the distance ladder. And I purposely did not, like radar astronomy gives us a solar system that actually gets us to parallax for the nearby stars. The parallax of Cepheids, like for example, the polar star gets us how we can calibrate the Cepheids off. That gets us to nearby galaxies. If we get beyond what we can see Cepheids, we try to find supernova. Crucially, we try to find if we find a supernova in a nearby galaxy, we go get its distance with Cepheids, so they calibrate off each other. And these two calibrate if we do our distances to this redshift. So that way, starting with radar astronomy, starting by figuring out what the distance between the Earth and the Sun is, we got that really accurately. Our parallaxes are accurate. Our parallaxes are accurate. Our Cepheid distances are accurate. If Cepheid distances are accurate, our supernova distances are accurate, and our redshift distances are accurate. So if I make an error anywhere along the line, it propagates all the way through. So a lot of science works this way, right? Where we have one technique that works here, and we calibrate the others on it so that we can use them on bigger distances or longer time scales or you name it. So a lot of information is calibrated. As long as you get it right the first time, the error doesn't you don't have a knock-on effect. But you can. So we had a whole fight on how far the LMC actually is because those Cepheids calibrate into the supernova direction. So we'll talk about that again at the end of the semester. Okay, so that's how we get distances through the whole universe. And Drew keeps dimming the whole dome because he wants to get to the actual fun part.
because you had pretty pictures up there and we couldn't see.
But I'm also knowing that this is the part where I'm actually through. Just to give you an idea, it also gives you like a time scale, right? So if it takes how long to travel throughout the solar system, that is in terms of days and weeks. If you talk parallax, it takes years up to centuries for that kind of light to get up to us. If you talk Cepheids, it's millennia to millions of years, right? It took the light millions of years to get to us. So travel time sort of also translates into how long ago are we looking. So if I look at the sun is 8 minutes ago. It's not so 8 minutes ago, that sounds a little disparaging, but if you look at the sun, it took the light 8 minutes to get here. Well, if I look at Pluto, the light took almost 24 hours to get here. If I look at Alpha Centauri, it was now a picture that's 4 years old. So if I'm looking at millions of light years away, I'm talking galaxies like they looked a million years ago. Now, these things move slow, so maybe they don't look that much different. But if I'm starting to talk millions and billions of years, I'm actually starting to look seriously back in time, like how things looked in the distant past. So I have my own time machine as long as I know how far away the thing actually is, because I can actually look at baby pictures of the universe, baby pictures of galaxies and stars, if I look far enough away, so far enough back. So we end up with eventually 13 billion years, that's the age of the universe, but it gives us a time machine to look back. So our distance ladder, if people talk about the distance ladder, is how we bootstrap our way out from radar astronomy to parallax to Cepheids to supernova to redshifts, and that's how we get from the solar system to the whole universe. That's how we pulled ourselves up. Not like von Munchausen, we basically said, yes, I pulled myself and my horse by my own bootstraps, but we managed to get there. Okay. This is for the end of the semester, but it gives you an idea, like if we do the redshift thing on galaxies, we start to see maps like this. And this is the very first one that was made that way. This is one of the more recent ones that were made that way. And so we can get maps of all the galaxies with distances and if they behave in big clusters and clumps. But that is fun to show on a slide. It is much better to show on the dome. So I'm now going to transfer to where I'm gonna talk from the dome. So if I try to do that up front, it's, I'm gonna fall out, so. Stop the recording because this does not translate well.